All right. How could I go about finding the length of segment OG? What could I use to find that length? What kind of a triangle is this? It's a right triangle. How big is this segment? 25. How big is this segment? 60. Remember, when we have a diameter or a radius intersecting a chord at a right angle, it is bisecting it. So this would be 60. So how can I find the length of segment OG? Pythagorean theorem is absolutely correct. Yes. All right, so we're going to do a squared plus b squared equals c squared. What should I put in for c? OG, that is what we are looking for. So OG squared. What should I put in for a and for b? 25 and 60. So I'm going to have 25 squared plus 60 squared. What is 25 squared? 625. 60 squared? 3,600. 3,600. And then we need to add those two together. What do you get when you add 625 and 3,600 together? Thank you. 4225 is equal to OG squared. And then what do I still need to do to figure out how big OG is? Square root. If you do it to one side, you got to do it to the other side. We're doing this to get rid of the squared on the OG. And what is the square root of 4225? 65. So OG is 65. There's our first piece. Next, we are supposed to find the length of OJ. Here's OJ. I'm going to go ahead and add what we just found for our radius onto our picture. From O to G is 65. If from O to G is 65, what's the length from O to K? 65, because that's another radius. What's the length from O to A? 65. What's the length from O to B? 65, because that's another radius. From O to C? 65. From O to D? 65. All of our radii have a length of 65. We're trying to find this length right here from O to J. Well, what is this right here? It's another right triangle. What could I use to find the length from O to J? Pythagorean theorem again. So a squared plus b squared equals c squared. What should I put in for c? OJ, this right here is my hypotenuse. 65 is my hypotenuse, because that's the radius. Remember, O to C is 65, but we're going to try to find the distance from O to J. So we're going to put 65 in the place of C. What should we put in for A and for B? $52 goes in for one of them. Doesn't matter which. So what should I put in for the other one? OJ. So I have 52 squared plus OJ squared equals 65 squared. Well, I know from the problem that we just got done with that 65 squared is 4225. So I can go ahead and write that down. What is 52 squared? You said 2704. So then I'm going to subtract 2704 from both sides. That gives me OJ squared equals what? What is 4225 minus 2704? $42.25 minus 2704. What do we get when we subtract those two? $15.21. And then we square root both sides to make our squared cancel out. And that gives us that OJ equals what? 39. So segment OJ has a length of 39. Last one. I want to know how long segment BG is. This entire thing right here. How can I find that length? What'd you say? Multiply the radius by 2 or add 65 twice. Either one, it's the same result. Absolutely. So we're going to do 2 times 65. What is 2 times 65? 130. Thank you. Wonderful work on the warm-up there, guys. We are going to hop back into your notes for the rest of today. We're back on page 10. We did the top half yesterday. We talked about what it means to be a tangent line. And we talked about how to check to see if something is a tangent line. If something is tangent, like I'm looking here at this picture in number 4, part B, BD right here is tangent to my circle C. So what's happening right there at point B? This is tangent to my circle. So what happens right here? What kind of an angle is that making with my radius? A right angle, yes. And that's what it says right here too. So that's telling me that BD is tangent to circle C. A tangent line will be perpendicular to a radius, forms a right angle with the radius. All right. So yesterday, we talked about 2 properties of tangent lines. The first one was that a tangent is perpendicular to the radius at the point of tangency. The second property, and we didn't practice anything with this yesterday, is that if I have 2 segments coming from a common exterior point, so now I'm looking at number 4, part A. If I have 2 segments, like this top segment here and this bottom segment here, and they're coming from a common exterior point right here. Two segments coming from a common exterior point. that are tangent to my circle. These two are tangent. If I were to draw in a radius, it is forming a right angle. If I draw in my other radius, it is forming a right angle here. So two segments coming from a common endpoint that are tangent to my circle are congruent. So this top segment here is congruent to this bottom segment here. And what can I do with things that are congruent? I can set them equal to each other, yes. So I would have 2x minus 9 is equal to 3x minus 15. And then we can solve this for x. What's the first thing I need to do to solve this for x? Get the x's on the same side. So I'm going to minus 2x from both sides. Don't forget to bring your negative down. So I have a negative 9 over on the left. 3x minus 2x is 1x, and then minus 15. Need your head up for me, dear. Then what do I do? Add 15 to both sides. What is negative 9 plus 15? 6, yes. So x is 6. Let's come over here and look at part B. So we already know that BD is tangent to circle C because BD is perpendicular to BC. What would we call BC here? What part of the circle is that? That is a radius, yes. Then it goes on to tell me that AD is perpendicular to AC. So AD, this segment right here, is perpendicular to AC, which means we would call AC what? A radius again. So because AD is perpendicular to AC and AC is a radius, I know that AD is tangent to circle C. So I have two tangent lines. What does that mean about those two tangent lines? They are congruent, yes. So this one is congruent to this one. What do we know about all the radii in a circle? They are congruent. So BC is congruent to AC. All right, let's see what other information they give us. Here it says that BD is 6x minus 17. So I'm going to add that to my picture. 6x minus 17. BC is 43. AD is 67. And AC is 4y minus 5. We're supposed to solve this for x and for y. What did we say we knew about these two tangent lines? They're congruent. So what can I do with their measurements? I can set them equal to each other. Absolutely correct. So I would have 6x minus 17 is equal to 67. And now we're going to solve this for x. So I'm going to add 17 to both sides. So that would give me 6x equals what? What is 67 plus 17? 84. And then we're going to divide both sides by 6. And 84 divided by 6 gives me what? 14. So x is 14. Right, there's half of what they wanted me to find. How do I find y? Set the radii equal to each other, yes. 4y minus 5 is equal to 43. So then I'm going to add 5 to both sides. That would give me 4y equals what? 48. And then we're going to divide both sides by 4. What is 48 divided by 4? 12. So y is 12. X is 14, and y is 12. Radii can always be set equal to each other if they're in the same circle because all the radii are congruent. And two tangent lines, as long as they're coming from a common exterior point, are congruent to each other. So we can set their measurements equal to each other. So far, so good? All the problems on your homework that look like ice cream cones, kind of like these guys, falling over ice cream cones. This is how you solve those problems. Right, let's look down at the bottom of the page. One of the applications of tangent lines. Here, I have a circle that is inscribed inside my polygon. On part A, my polygon is a triangle. On part B, I have a quadrilateral. We're going to look at this using properties of tangents. So I want to start looking on part A just at these pieces. I'm going to ignore for the time being these other segments off of here. That looks a whole lot like what we were just doing. That kind of has that ice cream cone look to it, right? What do we know about these two segments, KM and KN? They're congruent because they're both tangent to my circle. So I'm going to go ahead and mark them as congruent, which means KM is how big? 7. Yes. All right, now we're going to do the same kind of thing over here. I'm going to pretend like I can't see any of this for right now. I have that same kind of ice cream cone thing going on. So what would that mean about my top segment and my bottom segment? Yes, JM is congruent to JP. So how big is JP? 14. So what do you think that means over here? Yes. NL is congruent to PL. So NL would be how big? 11. Beautiful. They want me to find the perimeter of triangle JKL. How do you find the perimeter of an object? You add all the sides. So we're going to add all the little segments together. So my perimeter is equal to, I'm going to start here and work my way around. So 14 plus 7 plus 7 plus 11 plus 11 plus 14. Have I gone all the way around? Have I grabbed every single number around that triangle? Yes. So now I need to add those together. What is 14 plus 7 plus 7 plus 11 plus 11 plus 14? $64 is absolutely correct. All right, last one on this page. I have the same kind of idea going on with this quadrilateral over here. Let's look at just one part of it for right now. I'm going to look at this piece and this piece, pretending that I can't see any of the rest of this right now. What do I know about these two segments? They are congruent, yes. So if this one is 5.1, this one over here would also be 5.1. So what would that mean about these two segments? They are congruent. So this is 6.5, and this little bit right here is 6.5, but they tell me that whole side is 15.1. Do I have the ability to figure out how big this is right here? By doing what? Subtracting. We're going to do 15.1 minus 6.5, which would give us how much? 8.6. So that is the length of this segment right here, which is exactly the same as what other segment? What else is 8.6? The other side of it right here where it's touching. They have that common external point. So from here to here is 8.6. So if that is 8.6, how big is this? And I know I didn't make them touch, I should. 4. So how big is this? 4. Do I have enough information now to figure out how big this quadrilateral is? Yes, we're going to add all of those pieces together, all 8 numbers. So my perimeter is, where do you guys want to start? Give me a starting place. 4, sounds good. Let's start at this 4 right here, and we'll add around this way until we get back to this other 4 over here. So 4 plus 5.1 plus 5.1 plus 6.5 plus 6.5 plus 8.6 plus 8.6 plus 4. Need a little bit more room to add my plus 4 on the end. There we go. Now I have to add all of those together to find my perimeter. I'm curious, because we got quite a few numbers here. We've got 8 different numbers. I can put all 8 numbers in my calculator, but the more numbers I put into my calculator, the more chances that I enter a number incorrectly. Does anybody notice a pattern with our numbers here? How many 5.1s do we have? 2. How many 4s do we have? 6.5s? 8.6s? So I could do 2 times 4 plus 2 times 5.1 plus 2 times 6.5 plus 2 times 8.6. I don't have to. You can put all 8 numbers in your calculator if you want to. Or I could double each of these. That would be 8 plus 10.2 plus 13 plus 17.2. And now I would only have 4 numbers to put into my calculator. No matter how you decide to put this into the calculator, you get an answer of what? 48.4. Very nice work. right. That finishes up everything that you need to complete your homework. I'm going to start just a little bit on the next section, just a little bit, and then we will continue working on that tomorrow. We're only going to work for about, say, 5 minutes or so on the next section. And then you guys will have the rest of the time to continue working on your homework. All right, so next page, page 11 now. We are going to define another new term. This is called a secant. A secant is a segment or a line that intersects a circle at 2 points. So something like this. I'm going to call this point right here A, and this point right here B. Line AB goes all the way through my circle, and so that would be a secant. What would we call just segment AB where it stops on the circle? If I had drawn it like this, what would we call a segment like this? A chord, yes. So segment AB is a chord, line AB is a secant. So a secant is what happens when my chord extends beyond the edges of my circle. Chords stop at the circumference, and secants continue on. All right. So chords and secants can intersect inside my circle, like this picture, or they can intersect outside my circle, like this picture over here. If my chords or my secants intersect inside my circle, I'm going to go ahead and label these angles. 1, 2, 3, and 4. The measurement of angle 1, this angle right here, is equal to 1/2 the measurement of arc AD plus the measurement of arc CB. So arc AD. Angles 1 and 3 are congruent because they're vertical angles. And I need both of the arcs that are opposite my vertical angles. How would I find the measurement of angle 2 then? What arcs would I have to add together? So it'd be 1/2 of which 2 arcs? Those are my angles. 2 and 4 are my angles. That's okay. AC and, sorry, let me write this down. AC. So for angle 2, I would need this arc right here. And which other arc? BD. Beautiful. So when my chords or my secants intersect inside the circle, I add the arcs that are opposite that and its vertical angle, and then I cut them in half, and that gives me the angle measurement. If I have an arc, or sorry, if I have 2 secants that intersect outside of my circle, so I have an exterior angle, this angle right here, the measurement of angle M is equal to 1/2 times the measurement of arc OQ minus the measurement of arc NP. So this first arc will be the farthest from my angle. The second arc, which will be smaller, is the closest to my angle. That's where we're going to stop for today. You guys have the rest of our time, it's a little bit less than 10 minutes, to work on the homework that is due tomorrow. Homework number 5. So from yesterday's lesson, you could do 6, 8, 9, 10, and 12. And so the remainder of the problems come from today's lesson. So the first 5 problems are for the top half of the page, and the bottom 6 problems are from today's lesson.